Okay, section 5.5. This has to do with permutations and combinations. This will be the last section in chapter 5 that we're going to do. First thing, definition of a permutation. A permutation is an arrangement of objects in a definite order. Order is important. That's the first thing you're going to realize on this. So let's do an example here. Let's say I want to find all the permutations for the three letters A, B, and C. Well, I could go A, B, C, or I could go A, C, B. Those are different permutations. It's the same letters, but they're different permutations because it's a different order. If the B came first, I could follow that with A and C, B, A, C, and then you would have B, C, A. These would be the two where B comes first. And if C came first, you could have C, A, B, and C, B, A. And those are the different ways that you could write them, the different orders. So how many of them are there? There are 6 altogether. Now, a lot of times I just need to know how many, and I don't have to list them all out. Most of the time, that's going to be the case. So when that happens, this is what I do. I draw 3 lines, and each line stands for a place where I'm going to put a letter. So when I look at the first one here, how many different letters could come first? Well, A could come first, B could come first, C could come first. So that number is going to be a 3. Then we go to the second one. How many different letters could come here? Well, whatever I put first cannot come here, so that leaves only 2 possibilities. And then when you go to the third spot, there's 1. 3 times 2 times 1 is 6. That's the easy way on doing permutations. Okay, here it says, find the number of ways 6 people can arrange themselves for a picture if everyone is standing in a straight line. So using what I did here, I've got 6 people, there's 6 spots. So I draw a line for each one of those. So we go to the first spot. How many different people could come first? 6. But once you pick somebody there, there's only 5 for the next one, and then 4, and 3, and 2, and 1. And when you multiply all those out, I believe that's 720. Example 3, how many ways can 5 people sit in chairs arranged in a straight line? 5 spots. 5, I'm going to put dots. 5, 4, 3, 2, 1, and those multiply to be 120. We see this occur quite a bit where you start with some number, like here I went 3, and then it just goes down 1 each time, and your last number is a 1. Here I started with 6 and went down 1 each time and got a 1, and then here I started with 5 and got a 1. When you see that, since it happens often, these are called factorials. So 5 factorial simply means you start with 5, and then you're going to go down 1 each time, and the last number is always a 1. 6 factorial means 6, 5, 4, 3, 2, 1. And 3 factorial is 3 times 2 times 1. And actually, you'll get to a point you'll get these numbers memorized. 5 factorial is 120. 6 factorial is 720. This is going to be 6. If you had 4 factorial, that's going to be 24. And even if you went up to 7 factorial, that's going to be, I just had it, 5. It's 5,000. 5,040. I had to think about it for a second. I got it memorized. It just, I hadn't worked with it for a while. But you'll see those numbers over and over again. Okay, so here's a different situation. So how many ways can 6 people sit in 4 chairs? So I've only got 4 spots. We don't care about the 2 that aren't sitting. So in the first chair you got 6, the second chair you got 5, the third chair you're going to have 4, and then 3. So we don't get to the 2 and the 1. We're simply going to multiply those out. 30, 120, that's 360. Symbolically, we got some notation. This is the number of permutations of 6 items taken 4 at a time. 6 people, 4 chairs. And we see this quite often. So if I had the number of permutations of 4 picking 2, that means you're going to have 4, and there's going to be 2 spots, so 4 times 3 would be 12. The next one, you're going to have a 6 that starts it, and there's going to be 3. That's what the 3 tells you. 6, 5, 4. That's 120. And this one means 8, and you're going to have 4 of them. 8, 7, 6, 5. Whatever that is. 56, 280, 280, 6, 0, 48, 1680. Okay, now I'm going to throw something else in here. Some books will write the notation like this. The older books, and I catch myself doing this, so permutations of 4 picking 2, they'll write them as subscripts, the 4 in front and the 2. These mean the same thing. If I ever write something down, just know that's what it means. The book uses this, so that should be good enough for you. Okay. Special permutations. I throw these out because sometimes they pop up. How many distinguishable permutations are there using the letters in the word soccer? Well, see, here's the problem with the word soccer. We come up here. Soccer. S-O-C-C-E-R. Okay, I'm going to change the letters around a little bit. I'm going to start with the S. I'm going to put the O. I'm going to take that C and I'm going to put them here. I'm going to take that C and put it here, and then the E and the R. So I switched some letters. But if I wouldn't have told you that, you're going to say, well, those are the same. So that's why we call these distinguishable permutations, because you cannot distinguish that. Okay, so go back to our logic of what we did earlier. Okay, so with 6 letters, I would have put 6 blanks, and that actually would have been 6 factorial. 6, 5, 4, 3, 2, 1. 6 factorial. But since I had 2 C's, I've got to divide that. So 6 factorial is 720 divided by 2. That answer is going to be 360. Since I repeated the C's, there's 2 of them, I got to divide by 2. You actually divide by 2 factorial, but 2 factorial is 2. Okay, so here's one of my favorites. How many distinguishable permutations are there using the letters in the word Mississippi? So what you have to do first is say, well, how many letters are in Mississippi? I've already counted them. There's 11. So I'm going to put 11 factorial on top. Then there are 1, 2, 3. There's 4 I's. So I got to divide by not just 4, but 4 factorial. And then there's 4 S's, so I got to divide by that. And then there's 2 P's, so I've got to divide by that. Now, if you were working this out and just using paper, you could take 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. And it's times 1. I'm not even going to put it there because the 1 doesn't change anything. And on the bottom, we had 4 factorial, so it's 4, 3, 2. And another 4 factorial, 4, 3, 2. Again, I'm not putting the 1s because when you multiply by 1, it doesn't change anything. And then 2 times 1, which is just 2. Now, if you don't know the easy way of using a calculator, what I would do is I'd start crossing out. So see the 4, 3, 2 on the bottom here? That cancels that. Then if you take 3 times 2, that cancels 6. And then you got 4 times 2 cancels 8. So now you're down to 11 times 10 times 9 times 7 times 5. I don't know what the answer is. I guess I could do that real quick. 35 multiplied by 9 is 315. Multiplied by 11 is going to be 4, 4, 6, 5. And by 10, that's going to be 44,650. You can do that in your head pretty quick if you know how to do it. Okay, so that was distinguishable permutations. That's just one of the specials. The second one is a circular permutation. This is important if you're a card player. How many ways can 4 people sit around a table? If you're playing games, sometimes the order is important. Okay, now before I go to that, I'm going to, let me get another piece of paper. Let me get away from that. Let's say that you had 4 people around a table. Person A sits there, person B sits there, C, and then D. And they all have a seat. Well, at first you're going to say, well, you got 4 different people for the first one, and 3 for the second, and 2 and 1. So that answer would be 24. But here's the problem. What if A, when they walked in the room, decided to sit over here? Instead of B being there, A is there. And B comes to this seat, and C comes to this one, and D comes to here. It's still A, B, C, D. They're in the same order, they're just different seats. So since they have 4 different places, we're going to take that 4 factorial up here, and we've got to divide that by 4, and that's going to end up being 6 for your answer. Okay, so back to my problem here. How many ways can 4 people sit around a table? So you start out with 4 factorial, and since there's 4 seats, that becomes 4 times 3 times 2. I'm not going to put the 1 over 4. The 4's drop out, and you get 6. If there's 6 people around a table, you can start with 6 factorial on top, and on the bottom you're going to divide by 6. So you get 6, 5, 4, 3, 2, all over 6. The 6's drop out. 5 times 4 is 20. 20 times 3 is 60, and 60 times 2 is 120. So those are circular permutations, because everybody can get up and move one place to the left or the right. Okay, and then the last one I'm going to talk about are ring permutations. So you get circular and you got ring. And when you try to visualize, they kind of come out the same way. But here's what you got. Let me go back to my other piece of paper here. So let's say we've got a key ring. And I got 4 keys. I could go A, B, C, D. You can treat this the same way as a circular, so if that were the case, you'd have 4 factorial over 4. But with a ring, you can turn it around. So if I did this, and I turn this circle around where D is over here, then C, and then B, and then A, these are actually the same because they were still on the ring. I just turned it around. So if that's the case, you've also got to divide by 2. So 4 times 3 times 2 over 4 times 2. The 4's drop out, the 2's drop out, and you're left with 3. Back to my example. So if I have 5 trinkets, I know I'm going to have 5 factorial on the top, just like I had the 6 factorial on that problem. On the bottom, I know I'm going to have to divide by 5, and I also know I'm going to have to divide by 2. So if you work all that out, the 5's drop out, the 2's drop out. The only thing left is 4 times 3, and 4 times 3 is equal to 12. Okay, here I'm back to my key ring that I did. So again, that's 4 factorial, and on the bottom you got to divide by 4, and you got to divide by 2, and the answer is 3. You know, if I have 10 keys, 10 keys means you got 10 factorial on top. On the bottom you got a 10 and you got a 2, whatever that's equal to. Okay, I think I'm going to stop there. So that will be 5-5 video lecture part 1.